So let's have a look. So first we need to find the critical points. Right, so to do that we get so this will be 0 wherever y equals to 0. Right, so we need these guys to match up. Okay, so now we have a whole line of critical points. Right, we have the x-axis is all critical points for this function. So already things are a little strange, right? We have infinitely many critical points. Okay, now when we write down our Hessian, right, our Hessian matrix so there's no x coordinate in here, right? So we're going to get 0. Actually, no, 0, 0, 0, 2. So the determinant of this will be 0 for all x. Right, so we are very much in this fourth case. Yes?
Because do you have to write the upside down triangle f is equal to that? Do you have to write that? Or
Yes. Yeah. So you have to write down your gradient calculation. And then set the gradient to 0. Okay, so this is kind of a weird situation. I want to spend a moment just looking at the geometry of what's going on. Show you, oh, yes, sure.
So the determinant is always 0 for like even any y also because the y is not dependent.
Yeah, the determinant is just always 0. It's just like super duper always 0. So we get no conclusion. Okay. Our second derivative test gives us no conclusion. But what does our actual thinking tell us? If we actually think through what this function is doing, what are these critical points?
Is that when it would be like a change of like direction?
Yep, there's going to be a change of direction. Yep, so along that line, you'll have some kind of a fold or change of direction. But what are these critical points? Are they mins? Are they maxes? They're minimums. Minimums? Show of hands for minimum? Yeah, okay, one guy's like, right? So they're going to be minimums. We've got this squaring thing, right? So this will always be greater than or equal to 0. The smallest it can be is when y is 0. So we're going to be mins. Okay? Now I want to show how these two examples are kind of going differently. Why is this test inconclusive?
0, y 0.
Right, so looking at the graph, we see this kind of sheet, right? It's like a piece of paper bent to touch y equals 0, right? And the issue with this is that there's no rate of change in the x direction, right? There's nothing going on in the x direction. And our second derivative test, it feeds off of information on what's going on in the x direction, right? We need these things involving the x direction to work. We need information in the x direction in order to classify these guys. This is what's called a non-generic example. Something has gone weird here, and the weirdness is that this is constant in x. So our graph is somehow picking up that this thing is constant. If we do some, oh yeah, if we look at the contour plots, right, we get this kind of weird contour plot as well. Right, our contour plots are straight lines. So there's no information in the x coordinate, which is giving us the failure or the no conclusion here. Okay. If we look at the situation with our first example, right, we have this crazy cone that just like blows up super duper fast, right? It's like blows up exponentially fast. And there we see that we have this distinct minimum, right? When we look at the contour plots there,
And then we can drop.
step size.
No, it stops at 1.
Oh, it stops at 1. Oh yeah, C stops at 1. So we want step size 1, I guess. Yeah, that'll do. So now we've got non-trivial information in the x direction and in the y direction. Right? We see that we've got some change. The contours are getting closer together in the x direction, and they're getting closer together in the y direction. So we get non-zero quantities everywhere. Okay, so that's a little bit about the failure of this example. Are there thoughts there, questions there? Yes.
How do we find the minimum?
Right, yeah. So if you wind up in one of these situations where you get no conclusion, then you have to actually look at the function. Right, you have to think, okay, what's this function doing?
Always
Right, so when we get somewhere where there's no conclusion, then we have to come up with an argument for that specific function. We have to come up with an argument that says, okay, squares are always positive, square roots are always positive, something like that. You have to come up with an actual reason for it to be a minimum. But this is a very nice machine that almost always works. Okay. So I want to do one optimization question using this kind of stuff. Sort of contrast it with the techniques that you would see in first year calc course. So we'll find a minimal surface area of like a rectangular prism, so a rectangular box or a rectangular thing.
Something like this.
So we draw a diagram of the thing. We'll see what the setup looks like. This. Okay. Often it's helpful to draw a diagram because it gives you a place to put your notation.
Something like this.
So we'll say that this length is the x length, y length, and z length. So we'll name the quantities so that we know what we're talking about. And I really like it when people say, let x be something, and then they state the units. So I say a length in meters. Then it tells me how these are supposed to line up with, you know, our volume being 8 meters cubed. Good to have that clearly stated somewhere. Okay, now we'll specify our constraint. Our volume should be 8. And now we should say what we're trying to optimize. So we want to minimize our surface area, so we'll call that some function S. And then we calculate out the surface area of the thing. So for each pair of variables, we've got 2 rectangles of that size. answer. And then there's just a little bit of an aside here. So this is sort of the kind of question that if you asked a toddler this question, if they're like this big, they could probably get it after playing with blocks, right? To get the surface area, like the smallest surface area given a particular volume, right? It should be very nice, it should be very symmetric, the thing should, look the same from every direction. So playing with this, you could probably come up with the minimum intuitively. So whenever you're given these optimization questions, it's helpful to think about what the answer ought to be going into it. Yes. Okay, so we've got our goal. We want to minimize this function. Okay. But we run into sort of a technical issue now. Our technical issue is that we only have a tool for 2 variable functions. Right now we've got a 3 variable function. So just like we did in our first calculus class, we will reduce the number of variables by incorporating the constraint. So we'll reduce the number of variables by incorporating our constraint.